Welcome back to AI.Code.Cast. Today, we're going to be doing a deep dive into set matrix zeros.
Yeah.
It's a classic problem that interviewers just love to throw at candidates.
Did a good one. It seems simple at first, but there's some really elegant solutions you can get into.
So can you set the stage for our listeners?
Sure.
What exactly is the set matrix zeros problem?
So imagine you have a matrix.
Yep.
It's basically a grid of numbers.
Okay.
And the rule is if you find a zero anywhere in that matrix, you have to set its entire row and column to 0.
Okay, so like if I have a 0 in the top right corner, then I'd zero out the entire top row and the entire rightmost column.
That's right.
Okay.
And to make things even more interesting, the challenge is to do this in place.
In place?
Yes.
What does that mean in this context?
It means you can't just create a whole new matrix to store the results. You have to modify the original matrix directly, and ideally without using a lot of extra memory.
Ah, I see. So it's not just about getting the right answer. It's about doing
efficiently.
Efficiently, yeah.
Space complexity.
Exactly.
How to manipulate the data structures cleverly.
All right. I'm ready to get my hands dirty.
Okay.
Where do we begin with a problem like this?
Well, let's start with the most straightforward approach.
Okay.
Often called the brute force method.
Brute force.
It might not be the most efficient.
Gotcha.
But it helps us understand the problem better.
Okay.
And it'll set the stage for more optimized solutions.
So let's break down this brute force approach.
Right.
If we weren't worried about being super clever, how would we tackle this?
So imagine just going through the matrix, cell by cell.
Okay.
If you encounter a 0, then you proceed to set every element in its row and column to 0.
That makes sense?
Yeah.
Just zero out everything in the same row and column is the 0 you found.
Yep.
So what's the issue with this approach?
The issue is redundancy.
Redundancy.
Let's say you have multiple zeros in a single row. With the brute force approach, you'd end up visiting and zeroing out the same cells multiple times.
Oh, I see. So if you had a 0 in the top left and another in the top right, you'd end up zeroing out that entire top row twice.
Exactly. And the more zeros you have, the more unnecessary work you do.
Okay.
This inefficiency becomes especially noticeable when you're dealing with large matrices.
Yeah, that makes sense. So brute force is kind of like painting a wall and then repainting the entire wall.
Right.
Every time you find a tiny speck of dust,
Exactly.
it gets the job done.
Yeah.
But not very efficient.
Not very efficient.
So how can we avoid this redundant work? What's a smarter way to approach this?
Well, think about it this way.
Yeah.
What if we could somehow remember which rows and columns need to be zeroed out without having to constantly recheck them?
That's a good question. Is there a way to do that without using a ton of extra memory?
You're on the right track.
Okay.
There are ways to do that.
Go.
For example, we could use sets to keep track of the rows and columns that need to be zeroed.
Sets. How would that work?
So you'd have 2 sets.
Okay.
One to store the row indices that need to be zeroed out.
Gotcha.
And another to store the column indices.
Okay.
As you iterate through the matrix, if you find a 0 at, let's say, row I and column J, you simply add I to your row set and J to your column set.
So it's like creating 2 checklists.
Exactly.
One for rows and one for columns. And every time you find a 0, you mark the corresponding row and column on your checklists.
Precisely.
Okay.
Then in a second pass through the matrix, you can simply check if the current cell's row and column indices are in their respective sets.
Okay.
If either one is present, you need to set that cell to 0.
That's pretty clever.
Yeah.
It feels a lot more organized than the brute force method.
Yeah.
We're not revisiting cells unnecessarily.
Uh-huh.
What's the catch with this approach, though? Is it the most efficient way?
Well, it's definitely more efficient than brute force.
Okay.
But we are using extra memory to store those sets.
Okay.
The space complexity of this approach is O(m) plus n, where m is the number of rows and n is the number of columns in the matrix.
So it's a trade-off. We're saving time by being more organized.
Right.
But it costs us some extra memory.
Exactly.
Is there a way to do this without using any extra sets or arrays? Like, could we somehow mark the matrix itself to tell us which rows and columns to zero out?
You're thinking along the lines of the most efficient solution.
Okay.
This is where things get really interesting.
Okay.
We can actually use the first row and column of the matrix itself as markers.
Wait, what? How do we use the matrix itself as markers? Wouldn't that mess up the actual data? in those rows and columns?
That's a great question.
Yeah.
And it gets to the heart of why this solution is so clever.
Okay.
Let me explain. Think of it this way. We can use the first row and first column as a kind of control panel to tell us which other rows and columns need to be zeroed out.
A control panel? That sounds interesting. How does that actually work?
Imagine this. If we find a 0 in, say, row 5, we can mark the very first cell in row 5, that's matrix 50, as a 0. This acts as a flag to remind us later that the entire row 5 needs to be zeroed out.
Ah, I see. So we're essentially using that first cell in each row as a signal.
Okay.
Well, what about the columns?
We do the same thing for columns, but using the first cell of each column. So if we find a 0 in column 3, we set matrix 03 to 0 as a marker.
So the first row and column become like a checklist of rows and columns that need to be zeroed out. It's pretty clever. But hold on, what about the very first cell, matrix 100? It belongs to both the first row and the first column. How do we know if it's marking a row or a column?
That's a sharp observation. You're right, we need a way to distinguish between those two cases. That's where a single extra variable comes in handy.
Oh, so we're going to use one extra variable to keep track of things. Doesn't that defeat the whole purpose of using the matrix itself as storage?
Not quite. Remember, our goal is to do this in place, meaning using constant extra space. One extra Boolean variable still fulfills that requirement. It's not dependent on the size of the matrix.
Okay, I'm following so far.
Yeah.
So how does this extra variable help us with the matrix 100 situation?
Let's call this variable first:0. We'll use it specifically to track if the very first column needs to be zeroed out.
So if we find a 0 anywhere in the first column, we set first:0 to true, right?
Exactly. That way, even if matrix 100 is 0, we know whether it's because of a 0 in the first row or a 0 in the first column.
I'm starting to see how all the pieces fit together.
Yeah.
So we go through the entire matrix marking the first row in the column as we find zeros. And we use first:0 to keep track of the first column specifically. Then what?
Then comes the fun part, the zeroing out process. We iterate through the matrix again, but this time we skip the first row and first column.
Makes sense. We don't want to accidentally zero out our control panel.
Precisely. For each cell we encounter in the second pass, we check if its corresponding row marker or column marker is set to 0. If either one is 0, we zero out the current cell.
So we're basically using the control panel to guide us as we zero out the rest of the matrix elegance. But what about that first row and first column that we skipped?
We handle those at the very end. First, we check our first:0 variable. If it's true, we know the entire first column needs to be zeroed out, so we do that.
And what about the first row?
We check if the very first cell matrix 100 is 0. If it is, we zero out the entire first row.
Wow. So we've managed to use the matrix itself as a storage mechanism without losing any of the original information. That's some seriously impressive space management.
It is, and that's why this in-place solution is so highly regarded. It achieves the same result as other methods, but with constant space complexity denoted as O1.
O1. So it doesn't matter how big the matrix gets, we're only ever using that one extra Boolean variable.
That's right. The amount of extra memory we use stays the same no matter how many rows or columns the matrix has. That's incredibly efficient.
I have to admit, when we started talking about using the matrix itself for storage, I was a little skeptical. But seeing it all laid out like this, it makes perfect sense. It's so clever.
It's definitely a solution that often elicits an aha moment once you grasp how it works.
Okay, so we've talked about the brute force approach and this amazingly efficient in-place solution. Are there any other ways to solve set matrix zeros?
Absolutely. There are other clever solutions worth exploring, each with its own pros and cons. For instance, we could use Boolean arrays to keep track of which rows and columns need to be zeroed.
Boolean arrays. That sounds a bit familiar. How would that approach work? Boolean arrays. That sounds a bit familiar. How would that approach work?
It's similar in concept to using sets. But instead of sets, we use two Boolean arrays, one for rows and one for columns. Each array would have a size equal to the number of rows or columns in our matrix, respectively.
So if our matrix is, say, 5 by 4,
Yeah.
we'd have a row array with 5 elements
Uh-huh.
and a column array with 4 elements.
Exactly. We initialize all elements in both arrays to false. Then as we traverse the original matrix, if we find a 0 at position I, we mark row array and col array as true.
Okay, so it was like those checklists we talked about earlier.
Yes.
But instead of adding items to a set, we're just flipping a switch
Right.
from false to true in these arrays.
Precisely. And once we've scanned the entire matrix and marked our arrays, we do a second pass. This time, for every cell at I, we check if either row array or col array is true. If either one is true, we set matrices to 0.
So we're essentially using these Boolean arrays as a lookup table
Yeah.
to tell us which rows and columns need to be zeroed. It feels very systematic. How does this approach compare to the in-place method in terms of efficiency?
Time complexity-wise, it's quite comparable. We're doing 2 passes through the matrix, which gives us OMN, where M is the number of rows and N is the number of columns.
So similar to the in-place solution in terms of time, what about space complexity?
Ah, there's the trade-off. Since we're using 2 extra arrays, our space complexity becomes OM plus N.
So better than the brute force method,
Mm,
but not quite as space efficient as that super clever in-place solution.
precisely. But this approach offers a good balance between efficiency and clarity. It's very intuitive to understand and implement.
It feels like a solid option to have in your toolkit,
Yeah,
especially if you're prioritizing code readability.
I agree. It's a valuable solution to be aware of, particularly in situations where the extra space used by the arrays isn't a major concern.
I'm really starting to see the nuance involved in algorithm design.
Yeah,
There's not always one best solution.
right.
It's about choosing the right tool for the job,
Exactly.
considering both time and space efficiency.
That's a really good point. It's so true. This deep dive into set matrix zeros has been eye-opening. We've gone from the straightforward brute force approach
Yeah.
to the clever in-place method, and even explored solutions using sets and Boolean arrays. It's amazing to see how many different ways
Oh,
you
yeah.
can solve the same problem.
It really highlights the creativity inherent in computer science. And remember, the journey of problem solving is just as important as the destination. Understanding the trade-offs, analyzing the efficiency, and even just appreciating the elegance of a solution, it's all part of the learning process.
Couldn't have said it better myself. Huge thank you to our expert for guiding us through this problem so thoroughly. And to our listeners, we hope you've enjoyed this deep dive into set matrix zeros on AI.Code.Cast. Keep those algorithms running smoothly, and we'll catch you in the next episode.